Okay, so let's begin this video with an example. 4 students are working on a writing assignment, and they need to exchange drafts with each other in order to give and receive peer feedback on their work. And the question here is, how many ways can this exchange of papers be done? Right, so to give you an idea of what this question is asking, we have your 4 students here. Let's call them A, B, C, and D. Or maybe I'll call them numbers instead. Student 1, 2, 3, and 4. And then we want to decide how they can switch papers so they can give feedback to other students. Now, they don't necessarily have to switch papers in pairs. Right? So student 1 can get the paper of student 2. Student 2 can maybe get student 4, 3, 1, 4, 3. Right, so that's one possible way of each student getting a paper that's not their own. Now, well, how many other ways are there? How are we going to count this systematically? Well, this particular scenario is small enough that you can actually list them all out. We can start by listing all of them that has 1 giving feedback to 2. So you can have 2. Can we do 4 again here? No, we can't, right? Because 3 and 1 can't happen, because that will mean 3 gives feedback to themselves. So let's remove that. We can put 3 in here. And here I have either 1 and 4, which again can't happen because 4 can't be in the last position. So it's 4 and 1. And then finally 2, 1. And here we have, let's see, 3, 4 or 4, 3. So it must be 4 and 3. Right, and so you can keep going here and list them all out. And sure, you can try. And I'm just going to tell you that you should get 9 as the answer here. But what we really want to do here is to solve this problem systematically such that we can do the same calculation with more students, right? What if we had, say, 10 students instead, or maybe 100 students? You're not going to be able to list them all out. And so let's think about it in this way. What do we really want to happen, right, when we're doing this exchanging of papers? We don't want student I to get their own paper. So in a sense, if you think about this assignment, right, each assignment here really is a permutation, right, of the numbers 1 to 4. What we're doing is we're counting the number of permutations where I is not mapped to I for I equals 1 to 4. Well, okay, so how are we going to make this systematic? I'm going to say let AI be equal to the set of permutations, and in this case, permutations on 1, 2, 3, and 4, where I is not, or where I is mapped to I. Right, just so we're not confused here, right? I'm going to use the set to describe those permutations where I is indeed mapped to itself. And what we're really interested here is, so we want to count what the cardinality of A1 complement intersection A2 complement, A3 complement, and A4 complement. Right? So this makes sense here, right? Because if AI is the set of permutations where I is mapped to itself, then AI complement is the set of permutations where I is not mapped to itself, right? It's the complement. But this should remind you now of your formula for the principle of inclusion-exclusion, right? So we can use that to count the intersection of the complements of these sets. And so by the principle of inclusion-exclusion, this is equal to the following. So let's call that n. So remember, we're starting with the universe, all the permutations with no restrictions. We're subtracting all cardinalities of each set taken one at a time, adding back all pairwise intersection cardinalities. All right, and there are 6 of them here, because it's 4 choose 2. Subtracting all triples, and there are 4 of them here, 4 choose 3. And finally, adding back the intersection of all 4. So, what are these cardinalities equal to? Well, the cardinality of a single set here is equal to, okay, what is this doing? I is mapped to I in AI, right? So if you imagine this as A, so let's do A1, right? Let's take a specific set. So the permutations in A1 must have 1 mapped to 1. And that's the only restriction, right? So anything can happen for 2, 3, and 4. So this means the number of permutations in A1 is 3 factorial, right? And that's just the number of ways of assigning 2, 3, 4 to these spots over here on the right. And this is true for all these singleton sets, right? That's also A2, that's also A3, and that's also A4. And now you can do the same thing for the pairs. What's A1 intersection A2 cardinality? Well, here 1 is mapped to 1 and 2 is mapped to 2. Now we have to decide what 3 and 4 are mapped to. So this is just 2 factorial then. And this is all pairwise intersections where I is less than j, and they're both in the range 1 to 4. Right? And you can continue doing this. Triples. Well, if 3 of these students get their own paper, well, the 4th student has to get their own paper as well. Right? So there's only one way that that happens, and that's just the identity permutation. And similarly, you also get 1 for the last one. And so when you plug in everything here on the right, you're going to get, well, the universe is 4 factorial. Then each singleton set has cardinality 3 factorial. There are 4 of them. Each pair has cardinality 2 factorial, and there are 6 of them. Each triple is just cardinality 1, so it's just 4. And finally, add 1 at the end. And this is 24 minus 24 plus 12 minus 4 plus 1, which indeed gives us 9 here. And what we just did here was to count what we call the number of derangements on a set of size 4. Right? So derangement as a term means it's a permutation where nothing is mapped to itself. Right? So 1 cannot be mapped to 1, 2 cannot be mapped to 2, and so on. And using the same technique that we applied here, you should now be able to extend this to count the number of derangements on a set of size n. And the answer is here. Right? This is the formula you should end up with when you do that same inclusion-exclusion, so please try it yourselves. And on the online encyclopedia of integer sequences, it's this sequence, 000166. Right? So this website is basically a repository of many interesting integer sequences, of which this is one of them. Right? So for n equals 4, we have this. So we can also call that d sub 4, the number of derangements on a set of size 4. For 5 is 44, for 6 is 265, and so on and so forth, which you can evaluate just using this formula. Right, so when you write out this formula, it's going to look like the following: n factorial minus n factorial over 1 factorial plus n factorial over 2 factorial, and so on. And I just want to end here by mentioning something quite nice about the number of derangements here, and something quite unexpected. If you look at, again, the formula here for d sub n, right, so k here is the index of summation, right? So this is the denominator here that's changing from term to term. Let's look at the fraction of permutations that are derangements. So the fraction of permutations that are derangements. Right, so we know that there are n factorial total permutations on a set of size n. So you can also think of this quantity as the probability that a random permutation is going to be a derangement. Right, so what are the chances that the permutation you get maps no element to itself? And so if you do this calculation, okay, so that's 1 over n factorial, and we have the same formula as above. So n factorial does not depend on k, right? So the n factorial in here, we can actually move that outside, right? It's just a constant with respect to this summation, and they cancel. And what we have here is just the summation, k equals 0 to n of -1 to the k divided by k factorial. All right, so that's 1 over 0 factorial minus 1 over 1 factorial, and so on. And if you remember your calculus, this looks like something, right? Do you remember what it is? If you remember your Taylor series, right? So these are your functions defined as series, as power series. Recall that the Taylor series for e to the x, centered at 0, right, also known as the Maclaurin series, is the series, I won't use n here, I'll use k as well, so k equals 0 to infinity of x to the k over k factorial, right? And this is convergent for all real numbers. So what does that mean for us? Well, look at the similarities here. What we actually get for the asymptotics here, for this fraction of permutations that are derangements, is that this is the partial sums of exactly this Taylor series of e to the x centered at a equals 0, evaluated at a specific value of x, which means x equals -1. Right? So it's this, whatever we're plugging into x. And what we can conclude here is that as n goes to infinity, this fraction of dn to n factorial, which is all permutations, actually tends to simply e to the -1, or 1 over e. Right? And that's pretty nice here. It's just one more scenario where this constant e shows up, right? You wouldn't know it would show up when you were counting these derangements and permutations, but here it is.